You're muted at the moment.
Yeah, I'm working on it. Thank you, Norm. Thank you so much, Norm. And thanks, Jared, for coming. This is really excited. I'm excited to give the introduction today, but also particularly excited to hear your talk. From what I understand from chatting with Jared, the talk will touch on kind of a bunch of different areas in the theory of quantum computing and what you can do with quantum computation and that sort of thing, and also machine learning and things like that. So I thought, since I only have 20 minutes, it might be most helpful if I focus on one of those. So today I thought I'd give a little bit of a tutorial on the theory of computability and also complexity theory. Hopefully this is also something that, for those of us who aren't theoretical computer science kind of people, might be kind of interesting independently as well, as people who work in the field of quantum computing. So I'll just kind of jump in and get started. So something that we think about a lot, particularly in quantum computing, but also in regular classical computation, is what sort of problems we can solve efficiently, right? And we care about finding algorithms to try to solve interesting problems without taking absurd amount of time. And that's what I'm going to talk about actually for kind of the second half of this talk. But the thing I want to touch on first is a kind of little more zoomed out or broader picture, which is this question of computability. So this asks what questions we can solve at all, even with an arbitrary amount of resources. This might seem like a little bit of a ridiculous question if you're not someone who's thought about this for a long time, because you might think if you have an arbitrary amount of resources, you can just solve any problem you might encounter. But it turns out this isn't exactly true, and I'll explain what I mean by that. But in order to explain that, we need to kind of more rigorously define what a problem is, okay? So today I'm going to talk specifically about decision problems. And what I mean by that are questions with a yes or no answer. We can look at this in kind of a mathematical way, which might look a little abstract and complex right now, but I'll give some examples that make it a little more clear. So suppose you have two sets, U, which is this big set, and then L is a smaller set, some subset of U. And another way of phrasing a decision problem is just, given some X, some member of this bigger set, you want to figure out whether X is also a member of this smaller set. That's a subset of U. Okay, so what does this have to do with decision problems? Look at it like this. For example, one decision problem we might ask is whether an integer is prime. Okay, so in this case, this big set U is the set of integers, and the smaller set L is the set of primes. And what we're asking is, given some integer, whether that falls into that smaller set of primes. Another question we might ask is related to this question of factoring, which many people are probably interested in, considering we're in a quantum computing seminar. But just asking what are the factors of a number is not a decision problem. We can kind of convert it into a decision problem by instead asking, does a given integer have any factor less than some value k? In this case, the big set is the integers again, and then the small set is those with factors less than k. And just in case people are curious, it turns out if you can answer this question, you can answer the sort of like the function question too, which is figure out what the factors are of the integer by just choosing various values of k, and then you can kind of like binary search and zero in on what the factor is based on whether there is a factor less than k or not. Okay, just a couple other examples. For example, we might take some like classical Boolean circuit and ask if there's some setting of the inputs that causes it to output 1. Or another question we might ask is, if we take U to be the set of all possible programs we might run, for example, on like a Turing machine, we might ask, will a given program ever halt or stop? So in this case, our smaller set L is the set of programs that halt. And this last example, this last question is one I want to dig into a little bit, because it really has bearing on this question of computability. So just to restate the question, kind of just in English, the question is, given a program and maybe some input to that program, will it ever halt, or will that program just kind of continue to run forever? It turns out Alan Turing, way back in the 1930s, came up with this pretty amazing theorem, which actually says that there's no algorithm F which takes as input, programs and possible inputs to those programs, and then always correctly decides if the pair of the program and the input halts. So another way of saying this is that the halting problem is undecidable. There's no algorithm you can apply that actually decides perfectly whether a program halts or not. This might seem a little bit crazy, like why is that? Like why is this a hard thing to do? And the proof is actually kind of succinct, but I don't think it gives too much of a nice intuition necessarily. So I'm just gonna kind of go and think about it this way. Say you wanted to design some such thing F, which takes in a program and some input and decides whether it halts. How would you do that? Well, maybe what F will do is it just takes the program that it's handed and it tries to run it. And then it just sees, after it runs it for a while, whether it stops. So maybe it runs it for 1,000 steps. And for a lot of programs, maybe the program has already stopped. And then you can say yes, right? The answer definitively is yes, the program does halt. But what if it hasn't stopped? Well, maybe it's because it runs forever, or maybe it's because you just haven't run it long enough yet. So maybe you run it for another 1,000 steps. Oh, it still hasn't stopped. You can kind of keep doing this forever. And unless you get into some cycle or loop or something, you have no way to conclusively say that it does or doesn't halt. It'll just keep going on and on and on forever, and you'll never necessarily come to an answer. Now, of course, this is just one way we could design this function f. There are other ways to do it, but the proof does show us that no matter how you design this function f, there's no such function that can always get the right answer here. But something I do want to emphasize is that, like I said, there are f that are, quote, like pretty good, right? So the fact that we can't get the right answer all the time doesn't necessarily mean that we can't get the right answer any of the time. And I think part of what Jarrod will be talking about today is, various problems in quantum computing that are maybe undecidable, but how we can use that as an indicator of what problems we might be able to pursue or where we might be able to come up with answers. Okay, so just to summarize that, I'm kind of going to finish with computability right now and move on to talking about complexity theory. There exist some decision problems for which no algorithm exists that can get the right answer all the time. And these are uncomputable or undecidable problems. But despite that, perhaps you can get the correct answer some of the time. And hopefully that's in the instances that you care about. And the last thing I want to emphasize, this being a quantum computing seminar, is that quantum computing doesn't actually change which problems are undecidable or not. So we, always kind of think about, oh, quantum computing is super powerful. That's why we all work on it. Maybe it can take some of these undecidable problems and make them decidable. But it turns out that's not true. And I guess I can explain that later. If people are curious, they can ask me a question. But yeah, it actually turns out that's not the case. Things that are undecidable whether you use quantum computing or not. So, okay, this idea of undecidability was discovered kind of in the early 20th century, kind of through the 1930s, and moving through the 20th century, people started to ask the question of, okay, more than just computability, how hard is it to solve problems? And particularly these two guys, Hardimanis and Stearns, founded the field of computational complexity theory by asking basically that exact question. At the beginning of their paper that founded this field, they have this quote, which I like a lot because I think it kind of very directly asks this question. It says that, you have computable or not computable problems, but one finds, however, that some computable sequences are very easy to compute, whereas other computable sequences seem to have an inherent complexity that makes them difficult to compute. And for the rest of the talk and the field of complexity theory, this is what we're going to kind of investigate. So in order to do that, we have to have some kind of mathematical definition of hard or easy, right? And the issue you might think, if you haven't thought about this before, is that it seems to depend on how big the problem is. So take a problem like integer multiplication. Multiplying integers that are like 10 digits long seems inherently easier than multiplying integers that are like 10,000 digits long. So how do we define whether integer multiplication is hard if it depends on the size of the problem? And so what those two gentlemen on the previous slide figured out is that what you should do is you should measure the resources it takes to solve a problem as a function of the length of the input. So in the case of multiplication, for example, we might take this length of the input to be the number of digits in the numbers that we're looking to multiply. So there are kind of two ideas of complexity that we might talk about. First of all, we might ask the complexity of an algorithm. For example, the schoolbook method for doing a multiplication, this is the one where you kind of like write down the numbers you're multiplying and then multiply each of the digits individually and then sum up all the results, that you learned in like 4th grade or whatever. This one, for example, has time complexity order n squared. So what this means is, that the number of steps you have to do to multiply these numbers using this algorithm scales as the square of the number of digits. But what we're actually going to focus on mostly today is not the complexity of the algorithms necessarily, or like specific algorithms, but we're going to talk about something more general called problem complexity. So what we mean by this is the complexity of the best algorithm for a problem. So for example, we might say that integer multiplication has a complexity of, say, n log n, because it turns out the schoolbook method is not the most efficient way of performing multiplication. There's faster ways, and n log n is the complexity of the best algorithm. So given this kind of like rigorous definition of what we mean by complexity, we can go through and kind of try to organize problems into these classes called complexity classes based on, based on their complexity. And what I'm going to do for the rest of my talk is just walk through a few complexity classes that I think people may find relevant or interesting, and also hopefully will be relevant for Jarrod's talk. So the first one that I want to talk about is a very simple class just called P. And what the problems in this class have in common is that the runtime of the best algorithm for those problems is polynomial in the length of the input. Some examples are sort of these what you might think of as like simple problems, like performing arithmetic, right, doing multiplication or other arithmetic operations, things like sorting lists or arrays, diagonalizing matrices, say, and lots of other common problems that we might implement in our day-to-day programming lives. The key takeaway about the complexity class P is summarized in this idea called Cobham's thesis, which says that problems are feasible if they're in P, right? So feasible is kind of this like hand-wavy heuristic term, but what we mean by that is that for reasonable lengths of the input, we probably are going to be able to do it on our just like regular computing resources. Now, of course, this idea has its limits, because remember, we're talking about with the complexity, we're talking about the scaling of the cost of doing an algorithm rather than the like explicit cost itself. So of course, if you're trying to diagonalize a matrix that's like 100 million by 100 million, that's still going to be really expensive. But the point is that that for reasonable problem sizes, you don't have an extreme cost. Probably, there's you might have large constant factors or something like that, but that's the idea. Okay, so we have this complexity class called P. The next one I want to talk to you about is called BPP, which is kind of similar to P, except we allow our classical computer, which is I'm representing by this robot, to flip coins. So it gets to use randomness, and it doesn't have to get the answer right all the time. So this kind of encapsulates the idea of a randomized algorithm. In particular, to be a little more formal, we'll say that this includes problems for which there are algorithms which return the correct answer only with probability greater than 2/3 over the random choices of the algorithm. The reason that this is kind of useful is we can just run that sort of an algorithm over and over and over, and by choosing different coin flips, we can get kind of arbitrary confidence in the answer by counting how many yeses we get and how many nos we get. An example of kind of a common algorithm that is in class BPP is primality testing for prime numbers. So there's a test called the Miller-Rabin primality test that is very likely to tell you correctly whether a number is prime, and if you run it many times, you can become very confident in that. I also wanted to note that in 2002, it was shown that there's actually also a deterministic algorithm that doesn't involve randomness. So testing for prime numbers is also in P. Okay, the next class I want to talk about is BQP, which is our favorite one. This is problems that have algorithms which run in polynomial time on a quantum computer. So in this case, our robot has an atom. Again, due to the inherent randomness of quantum algorithms, well, most of them, we allow our algorithm to return a correct answer with probability only greater than 2/3. Again, we don't need to get the answer right all the time, but we can again do this trick, or we just run it many times to become confident in the answer. And this class includes everything in BPP. Remember, that was the randomized classical algorithms, because we can always simulate a classical computer using a quantum computer. And it also has these problems like factoring and discrete log through, of course, Shor's celebrated result of Shor's algorithm. Okay, so I only have a couple more complexity classes that I wanted to mention that I think will be particularly relevant for Jarrod's talk. This one is one that people may not have heard of quite as often. It's one called p-poly. And what this means is it's a class of problems that have algorithms which run in classical polynomial time, but they get access to some extra information, which is called advice. It's called an advice function. So they don't need to figure out the entire answer on their own. They get to kind of crib off of this. You could think of it like a cheat sheet, like our robot has here. And the important thing is that this advice might be hard to compute. So if this advice was easy to compute, we wouldn't have to worry about p-poly. We could just say it was in P, because instead of looking at the advice, the algorithm could just compute the advice on the fly and then use it that way. But this includes instances in which that extra advice, that cheat sheet, may be super duper hard to come up with. As an example, I actually want to just very briefly mention how you can show that the randomized algorithms we talked about in BPP, any problem that has a randomized algorithm solution also has a solution that's in this class called p-poly. And you might wonder, okay, so how do we show that, right? How do we show that, given the fact that we have a randomized algorithm that flips coins to get the answer, with some high probability? How does that allow us to use an advice string to get the answer correct all the time? Because in p-poly, we don't allow this, probability greater than 2/3. We want it to be right no matter what. Well, it turns out what you can do is you can just take the BPP algorithm and figure out some specific sequence of coin flips. So some specific choice of the randomness that causes the algorithm to land in this 2/3 probability that you actually get the answer right. And regarding that top point that I had, that this advice might be hard to compute, of course, it's hard to come up with the correct sequence of coin flips that causes the algorithm to always land in this correct probability. But that's the point of this advice function, is that it can actually tell you what coin flips you need to make, what the results of those should be to give you a correct answer. Something that's really amazing, that even some undecidable problems, like we discussed earlier, can be in p-poly if this advice is uncomputable. So you can kind of like hoist the undecidableness of a problem into the undecidableness of the advice. And then if you somehow manage to come up with some advice that's undecidable, then you can solve even an undecidable problem. Okay, last one, because I think it might be on people's mind. I wanted to talk about the complexity class NP. What NP is problems that have answers that are checkable in classical polynomial time, given some proof. And what I mean by this is that there's some algorithm for these problems where if the correct answer is yes, there's some proof, which we'll call W, that when the algorithm takes in this proof and the instance that you're asking about, it says, okay, yes, you know what, given this proof, I'm confident that the answer is yes. But what we want is that if the answer is no, there's no proof that will actually convince the algorithm that the answer is yes instead. So no matter what the proof is, if the answer is no, we want the algorithm to return no. As an example, we can talk about integer factorization again. So this question of, does an integer have a factor less than k? And the proof is simply the factors of the integer, right? So if the integer does have factors less than k, and you hand us the factors, first of all, we want to multiply the factors you gave us together to make sure they actually multiply to the integer you were asking about. But then assuming that they do, you can just check if any of them are less than k. And then you can be confident if one of them is, yes, that's correct. But in the no case, there's no set of integers you can hand me that will convince me that that there is actually a factor less than k, because either you're going to hand me something that doesn't multiply to the integer we cared about, which would be, I would just immediately reject that, or you hand me a bunch of numbers that are all greater than k, and I say, okay, well, none of those are less than k, so again, I'm returning no. And just to kind of like nail down this difference, because P-poly and NP both involve, cribbing off of some extra information. I just want to make really clear what the difference is. First of all, in P-poly, the advice that you're getting is assumed to be good, in the sense that, you're not like skeptical about whether it's right. You're just being handed something and told this is correct. While in NP, the proof has to be actually checked by the algorithm. The other difference is that in P-poly, the advice that you get applies for all instances of a given size. So say you have some like integer, some integer of length, 1,000 bits. If there were a P-poly algorithm for that, that would mean that there's one string of advice that allows you to factor, all integers of that length. On the other hand, with NP, you get a unique proof for each instance, right? So for each integer that's 1,000 bits long, you get a unique proof, which is the set of factors of that specific integer. Okay, so that's everything I wanted to cover in my tutorial. With that, I'll move on to introducing Jarrod, our speaker for today. So Jarrod went to undergrad at Berkeley and got his BS in chemistry here, and then moved on to Harvard for a PhD in chemical physics. And Jarrod told me that apparently, when he was finishing his PhD at Harvard and getting ready to move on, that he was like talking to people about career paths forward, and they said, there's just not going to be any careers in quantum computing, so you should really, think about working on other things if you want to make sure that you're employed later. But Jarrod went on to become a fellow at LBNL, where he started working on quantum computing stuff, and of course now is working at Google Quantum AI and very much has a job in quantum computing. I guess was maybe hired by one of the people who had told him that there wasn't going to be jobs in quantum computing. So yeah, it's exciting, obviously, how our field is moving forward. And Jarrod, we're really looking forward to your talk.
Great. Thanks so much for the introduction. Here, let me share my screen real quick. Sorry, I couldn't hear anyone. Could people hear me when I shared my screen?
We weren't hearing anything once
you might have still been muted. We saw the screen perfectly, but I think you might have still been muted.
All right, strange. I think it disabled when I clicked share. Sorry, we usually use Google Meet. Give me a minute here.
That's fair. Makes sense. I think it seems that you're still muted somehow.
Yeah, at least it shows the mute sign next to your name.
We can like manually unmute you.
Let's see. I don't know.
Oh,
Sarah,
here we go. Ask to unmute. There we go.
Perfect.
Jarrod, are you able to talk?
Can you hear us, Jarrod?
Sorry, it appears to disable my audio every time I share my screen. Let me go to my backup computer really quick. Maybe this is
sounds good.
Sorry,
no
sometimes rejects.
No worries, no worries.
This. All right, let's go to. Let me try one more time before wasting too much
sounds good. I can also
time here. Why it's not allowing this. Maybe if I do whole screen instead. Let's try that.
I think this will work.
Jarrod? All right, I'm now on full screen.
Oh, amazing.
Perfect.
Works great.
Okay, great. Let's do that. All right, sorry for the technical difficulties.
No problem.
And thanks so much for the invitation to come give this talk, and thanks so much for the beautiful intro. Yeah, it was indeed a pretty funny story to sit around in graduate school and hear, oh man, if you want to get a job in this field, tough luck. You should work in something else. There's no jobs, not even academic. And then to be hired by more or less the same person a few years later, growing a large theory group in the area. So, things change rapidly. What can I say? So, yeah, I'm excited to talk to you guys today about a project that I think excited me for a number of reasons. It kind of played at this intersection of physical simulation and learning that I enjoyed quite a bit. And honestly, the project kind of changed my perspective on parts of science as well. So much so that it inspired a sort of more philosophical perspective that we wrote down recently, and actually gave a talk on that part of the topic to the Simons Institute relatively recently, which was a lot of fun. But I thought for today, I'd only touch on the philosophical bits a bit and kind of drill down, hopefully, into the technical part that inspired a lot of this recent work and revelations, at least for me personally. Whether there'll be a revelation for you, I guess we'll find out. So I wanted to start pretty general and a little bit philosophical, and then kind of dive down into what we actually did that led to some of these results. So I've shown this timeline a few times, and I think it somehow remains true, at least in its motivations, which is if you graph the excitement about quantum computing as a function of time, we of course have many dips and bumps as people get very excited about breaking encryption, and then maybe enthusiasm wanes a little bit because it's really hard to build the devices. Qubits start to get better and better, error correction and algorithms get better, and we start to build our excitement. And then we get some fun experiments like the sort of beyond classical experiments that our group has done and some other groups now have followed on as well. And now there appears to be this big chasm where we would like to move beyond these interesting sampling problems that sort of tell us about the fundamental nature of these computations, but in a way, they can't really be the foundation of what we do because we need these devices to be useful for something, whether that be scientific exploration or otherwise. And so we know a way in which one can go and error correct a quantum computer. We know a few ways, but that might be some time off. And in the middle, we're hoping to use these devices to reach some practical applications, even if it's very niche, but if a few people really need it and it's very useful, that would be great. And that's kind of the area that I think about. And I think that quantum simulation is, for example, one of the closer ones of these problems. But actually today, I'm going to say in the way that simulation and learning are related, I might have taken a slight step back from reaching practical applications because of the ways in which nature offers us data and makes this competition even harder than it would have been otherwise. So what are the early application areas that people talk about? People often talk about optimization, I think spurred, for example, by a lot of the excitement about D-Wave and annealing in early days, but I won't touch on that today. Machine learning is a recent one, and I think this is kind of funny because you can call almost anything machine learning these days if there's a probability distribution involved or something like that. But I hope that you'll think that my cast of what this means will be somewhat interesting and convincing, not only for what I'm talking about, but for science in general. And of course, quantum simulation, being the closest to the actual hardware that we're building, we think has some of the lowest abstraction overhead and might be one of the early applications of what we would do. But I want to take a kind of strange perspective on quantum simulation for a minute, particularly in the view of chemistry. So when in quantum computing, we often reserve the term quantum simulation. Not everyone does this, but some people reserve it for specifically the time dynamics that you would do for a quantum system. So you take some interesting quantum system, you evolve it forward in time, and you bound the error and check how expensive it is. And we think compared to classical computers, we are very, very good at this task. So this is one of these tasks in BQP that was mentioned before. So let me imagine for a minute that I was a chemist and I wanted to simulate chemistry, and what I had was my quantum computer or a classical computer, but I'd kind of ignored the last 100 years of physics or chemistry development other than this. So what might I do? I start with some set of reagents or input chemicals, and maybe I have a huge bath of them such that it's kind of effectively infinite, my reagent supply. And now I have some products that are going to come out of this reaction, might or might not. And I start asking myself questions like, how long does this reaction rate typically take? Or how long does this typically take? How many of them are produced? And does this ever happen? Might be another question I ask myself. So if that complicated product is large and strange, like an entire human being, you might imagine that's kind of a hard question to answer. And so if I know nothing of chemistry or anything else, I might say, okay, well, I have equations of motion for these atoms, or I have the Schrodinger equation and my perfect quantum computer that presses this forward in time. And sometimes maybe I can afford only to fit one copy of this interesting system. And I'm just going to put it in, and I'm going to wait, and I'm going to keep watching and measuring. And then if that product never comes out, I might have to wait a really long time, or I might not get any satisfying answer to that question at all. But if you're sitting in the audience, you're saying to yourself, perhaps this isn't how we do things, but perhaps at least quantum complexity theory has already told us a little bit about this particular situation. So if I imagine that simulating this system forward in time is what quantum computers do best, just kind of depicting how a charge on or excitation on a protein might move around on its backbone. And I can do that very quickly now on a quantum computer. Algorithms have gotten much, much better. And we can essentially get numerically exact evolutions for the purposes of refining error that's sublinear in the number of basis functions, which is incredible, really. But exact classical computation sort of has an exponential wall for this. So entanglement truncation in the very general case is challenging. But what you might wonder then is, okay, so if I'm just taking this dumbfounded view of chemistry and I'm marching things forward in time, hoping to compute faster than the lab, can my now quantum computer, which appears to have this exponential advantage over its classical counterpart, buy me something for this? So interestingly, there have been at least a few results telling us that that's not really the case. Even quantum computers have limits. And in particular, we have these, I'm going to kind of caricature it for now, but things like the no fast forwarding theorem that tells us very roughly that if I was to do this kind of simulation, basically the simulation time is always going to be greater than the physical time. And if I have a chemical reaction like rusting that might take hours to happen in appreciable amounts, and I'm only allowed like a single copy of the system, this is basically a very disappointing result. What can I do with this sort of simulation? And so now you're probably saying, okay, well, that's not how we do chemistry and physics. We've actually, stuck our heads up from the sand and looked around every once in a while, and we started to notice things. And in noticing things, we started to look at different ways to formulate some of these same questions. So if you're familiar with how the electronic structure problem is typically presented in either quantum computing or kind of chemistry talks, you'll often see this only the time independent version written, and something of the effect of how all of chemistry is embodied in this equation, and it's only much too complicated to be soluble. And we've really taken an implicit step here. In the most general case, maybe all I could really do is push myself forward in time, but I've said, okay, actually, in some cases, we can isolate these eigenstates, which might tell us something about the long time behavior of my system faster than it would take for it to go physically in time. And I'm thinking of things like transition state theories and many, in fact, theories from physics and thermodynamics that we use every day without thinking too much about the assumptions or information that went into them. I'm sort of boldly making an assertion in many cases that thermodynamically stable things are likely to appear, and I can sometimes find those faster than if I had just waited for a system to go forward in time. And so if I'm directly simulating chemistry, oftentimes I'm not referring to just doing time dynamics. I'm referring to taking some structure and then trying to build some understanding of it. But most of that understanding comes from some of these reduced models and observations. And I'm trying to kind of evidence that a lot of the things we're doing are not just computation, but are importing data from elsewhere. For example, when we look at these absorption spectra, we're often not doing strict time dynamics. We might be doing linear response. When we look at reaction rates, we're often looking at a thermodynamic quantity of a kind of transition state rather than considering all possible paths as would be most correct, for example, in a long dynamic simulation. And then we're taking those insights and we're trying to build them into our designs. And really the dichotomy I'm trying to show here is that this is not just taking an input system and running it forward in time. We're in fact being a little bit smarter because we realize, for example, the world isn't on fire, so all energy levels are not equally likely, or things like this. So then you might wonder, can we say something about the predictive power of free energies or any of these kind of reduced quantities that you might calculate on a subsystem? So if I just have this isolated molecule, I calculate its free energy, and now I'd like to make some blanket statement about it way far in the future. And interestingly, quantum computing and quantum computer science has answered some of these questions as well. In particular, questions like, does a system ever thermalize, kind of as you infinitely repeat it? Does a system have an electronic gap? Will molecule X ever form from constituents Y? At least a few of these have been proven undecidable, as you're kind of hearing about before. And I'm going to appeal to a definition by Chris Moore that's kind of a physical undecidability definition, which is to say that basically as a system evolves forward in time, there are sudden qualitative changes that cannot be predicted in any way except to evolve the system forward in time and see if it happened. And no answer in finite time can ever indicate it will never happen for all systems. So why am I kind of casting these problems in this way? Doesn't that seem a bit defeatist to claim that there are some problems for which there isn't an algorithm that can run forward in time or a quantity that will tell me something interesting about it? And I would say that actually the reason I want to say this is that maybe this is an interesting model for which to view some problems. If undecidability can formally be broken by advice in some cases, and data is a restricted form of advice, maybe we should think about the data we collect from experiments as more powerful than we currently do. And so that's kind of the philosophical preamble. And I'm going to show you now what sort of results more on a concrete level that led me to kind of be interested in questions like this. So taking a kind of dramatic turn now, let's step towards learning on quantum computers with variational algorithms. And so you might be familiar with some of these problems. So we often, I think the original motivation for us was simply we wanted something that would run on a quantum computer. And it has since been extended to many problems, including finding the ground states of molecules and other things like that. But the basic ingredients are you just have some quantum circuit or quantum state you can prepare with parameters. You can evaluate an objective and feed back a classical optimizer to try to do better and better on one of these circuits. You can do it with chemistry, optimization, nuclear physics, machine learning, etc. And let's see, to give you kind of a brief example of this, you can imagine from this circuit, which is an oldie but a goodie, as they say, you can view the quantum software as the circuit at the bottom of this screen. So you kind of just read like music notation from left to right. When you encounter an operation, you can look up at the top and see what's being done to the physical qubits. And eventually you just measure this objective function out. You'll loop and try to minimize some error iteratively with some set of parameters. Okay. So since that paper's been done, there's obviously been a lot of advances in this work. And I want to point out one in particular because I think it's going to help bridge the connection from physics to machine learning, hopefully for some of you. So we did another experiment studying chemistry systems where we tried to do have more variational parameters, and we kind of based things off an ansatz called Hartree-Fock, which if you're a physicist and not too familiar, perhaps you can just view it as optimization with free fermions with kind of a loop involved, but that part won't matter too much. This experiment was largely about error mitigation, but I wanted to bring the circuit back in order to sort of give you a basis for which to talk about. So this circuit acts on the space of n qubits, but in fact, it's this classically tractable approximation. So it occupies a very small part of that space and is in fact easy to simulate classically. But it's going to form the basis for what we do in a minute. So hopefully that kind of gives you a feeling for how one would implement it on a quantum computer, at least. So those are just rotation gates where I haven't told you too many of the details, but it's just to say that it involves n qubits, but a very small part of n qubits. And this analogy of viewing quantum circuits sort of as neural networks with trainable parameters has had a little bit of mileage for us so far. They aren't exactly the same. We don't have nonlinearities, and typically things aren't unitary. But it's been a fruitful study for us because we've already identified some issues like vanishing gradients that can happen, which were also detected in classical circuits as well. The only additional complexity is, of course, that you have to read out more in a Monte Carlo sampling sense, whereas in some cases classically, that function lets you do a lot better for precision. But what I really wanted to talk about with these circuits is that there is an enticing connection now. So we've started out with these variational circuits, which are just circuits and parameters that I'm going to train. And we'd like to move towards learning and machine learning and things like that. So there were these proposals. So I mentioned the vanishing gradient problem before, and classically that often occurs because you have activation functions that are kind of blowing up or shrinking your function very quickly in the depth. And if you have a very long neural network, like a recurrent one that could be called in principle an infinite number of times, wouldn't it be nice if the norm didn't grow or explode? And this touches base with what we, of course, know in quantum computing is if you made it unitary, you'd be guaranteed to have that norm conserved. And in fact, this is what several leading researchers in machine learning did, was to make what they called efficient unitary neural networks. And to make them work, you just kind of pile together because you still want that nonlinearity. So unitary, nonlinearity, unitary, nonlinearity. And it's sort of very suggestive of the fact that, you know, if there's a unitary component, couldn't we take one of these leading networks and just plug quantum in and magically everything would be better, right? And in fact, that efficient unitary neural network that I mentioned before is exactly the free fermion rotation or Hartree-Fock circuit that I mentioned. That connection wasn't made in the paper, but in fact, this is exactly what one implements. And so if we start with that Hartree-Fock circuit and just pile in some nonlinearities between repetitions, we at least start from a competitive classical algorithm, and then surely adding quantum to it can only make things better. So let's boost the power with quantum. So the classical case takes n inputs and has n outputs. And a natural choice, if I'm talking in this language of free electrons, is to have, say, a single electron distributed across these n modes and just have its expectation value be whatever this normalized input was. And now we're going to beef up the power with quantum, because as I mentioned before, just that circuit on its own is very easy to do classically. It's just kind of a trick of free fermion rotations. But now I'm going to make it less easy. So I've plotted, or I mentioned here the effective dimension, what's going on. So first, maybe I add some new particles. So I've started with my classical input. I put it on my quantum computer. I add some particles. I interact them. I loop, add some more, interact them some more. And basically, you can convince yourself that this is a universal quantum circuit and that you can kind of do whatever you want with this thing in the middle. So this should be very, very hard to simulate. Now I can either destroy some particles or I can just measure them and renormalize. And at the output, I'll have done some function to my classical input. And I'm like, okay, fantastic. This is a very hard quantum circuit to simulate. I've beefed it up with quantum. Clearly, we've solved all the humanities problems. So let's let our model, though, have a little data as a treat. This is a machine learning or learning problem after all. And so if I just have some data that I'm going to label xi as the inputs and yi as my outputs, maybe it's labels or regression, I'm going to put that into the quantum state in the way I said. So I'm going to stick it in the amplitudes, say just from 1 to p, where before I used n to keep you on your toes. And then I'm going to do an arbitrary length quantum circuit and code those labels into the output of this quantum circuit. And then I'm going to do it as the expectation value of some Hermitian operator O. And in fact, if I use ancillas as well, you can make this sort of into an arbitrary classical function. So this can be about as hard as you want it to be or interesting. And we know because this is an arbitrary quantum circuit, direct simulation of it, as in if I give you the circuit to evaluate and the operator and the inputs, should be at least as hard as BQP. In fact, it should be much harder because it's a very long circuit. But let's look at what that function looks like in terms of the inputs with this encoding that I've chosen. So I write it down, I do all this math, and I find that it's this interesting function where I've lumped a horrible amount of complexity into this coefficient BKL, but there's not that many of them. So that's interesting. And in fact, it's at most a quadratic function on the inputs with p squared coefficients. And generally from learning theoretic bounds, that kind of means that I'll probably need on the order of p squared data points to learn this exactly. And so somehow with node data, this was an arbitrarily hard quantum circuit. And with a tiny amount of data, it's an almost trivial learning task. And of course, this is a little bit of a caricatured case where I've put things stupidly in the amplitudes. But this kind of sparked, and this is kind of a real historical telling of how this came about, this kind of sparked an interest in, well, can we actually say something about when it would be hard, even as a learning task? If some amount of data breaks the difficulty of this problem, how do we know when that's going to be the case? Doesn't that make our classical competition a lot harder? And this is kind of the foundation of where this work went. And we worked to show certain additional facts in kind of a rigorous sense, that if you collected data from these quantum circuits and you compute a learning algorithm on them, you can show that in fact, this is a wider class of problems than the classical algorithms alone that you can solve. And I often get asked, well, then what's the difference between BQP and this class BPP SAMP that has data from quantum computers? In a learning context, it's sort of whether your learning algorithm requires the embedding itself to be quantum, or if you can get away with just having data. And the key example of this, as with many things in quantum computing, is factoring. So factoring sits squarely in BQP, but not BPP SAMP as we've defined it. So we wanted to develop this kind of test for problems. It was kind of a litmus test that says, okay, I know now that my circuit being hard isn't good enough. We also need to have it some other restrictions on the data that comes in, and particularly the geometry of the data. So I won't go through this whole flow chart, but the hope is to create a litmus test for saying when it's possible to even see a quantum advantage. So to do that, I'm going to take a detour through quantum kernel methods, and you won't need to know too much about them to follow this, hopefully. But kernel methods are methods where we want to take advantage of something that only requires some kind of pairwise proxy for distance or similarity, known as the kernel. And if I can evaluate that, I can plug it into a lot of well-known methods that take as input kernels and do all the fancy, classical machine learning that I would like. And the only definition of quantum kernel method is that similarity metric will be evaluated on a quantum computer. And hopefully it's something that's hard to do classically, otherwise, why would you? And to give you a brief background, what's interesting is that for some very simple kernel functions, so these similarity metrics, it implies a map to a higher dimensional feature space that might be very, very hard to do in that space by itself, but the similarity measure is very easy to compute in contrast. So that embedding that you imply might be some wild infinite dimensional feature map, and learn linear functions in this space might allow you to do very powerful things. In the context of quantum kernel methods, I think it's actually interesting, because if you imagine the most natural similarity measures for quantum states, you might imagine that it's an inner product between two states that I prepare with this data encoding. And in fact, if you look at what feature map this implies, if I just do a matrix of their overlaps as my kernel, you'll find that it misses the cross terms because you only get these sort of linear terms. And in fact, if you do an element-wise square of the individual terms, that changes your feature map to one that in fact can learn the observables. And there's other kind of nice features of that as well. But it's interesting because it lets you see from this quantum perspective how very subtle changes in this kernel map imply a much more powerful function that I can now learn given a linear classifier in this other space. And the other nice feature of kernel methods is they tend to be much more amenable to analysis and allowing us to prove things in kind of a learning theoretic sense. So let's set up a bit the model that we're going to talk about to kind of get to these results in particular. So I'm going to have some set of initial data that I'm interested in. In some cases, this might define an initial state, or it's a Hamiltonian for some ground state problem that I'm looking in, or for general data. And in fact, as I mentioned before, this could sort of be an arbitrary encoding circuit, but I'll call this part that puts my data into my quantum computer the encoder. And now I'm going to have some part at the end that's going to have a dividing surface in it. And I can either use kernel methods, or I can use what one would call a quantum neural network. And this tells me something like how magnetized was it, or tries to predict a reaction dividing surface or the like. And so the data will look something like xi, yi. And kind of these fun observations is that at least the quadratic quantum kernel is invariant to things like these quantum neural networks. And so with enough exponential amount of data, the quantum kernel is equivalent to an infinite depth quantum neural network, which I think is a fun fact. And so let's talk for a second about that first quantum kernel that I mentioned. Of course, you can define many similarity metrics that take advantage of a quantum computer. And one of them is fidelity, of course. But fidelity, when you think about it, for many qubits, is a bit of a weird metric. It looks kind of like a spike in all of Hilbert space. If you have, say, n qubit bit strings, and they're kind of differ by one entire bit flip, That's about as far, or that's exactly as far as that bit string then from things which have flipped n of them. So as you keep flipping, you keep getting no signal. These things make it very hard to kind of train these systems or get signal for a kernel method. And so some suggestions that I'll get into are, for example, local successive approximations based on reduced moments. And I know Seth and collaborators have worked on some quantum Earth mover distance that has kind of similar characteristics. But the idea is that you can kind of get more signal from reduced coarser observables before getting all the way to something like fidelity as a metric. And this is part of what motivated this projected quantum kernel that we talked about. So this is a different type of quantum kernel, which if you recall the quadratic one from before, where I'm taking inner products and trying to say something about their overlap squared, it can be really easy to accidentally end up with something that looks like memorization, meaning I put in a new point and it concludes it's similar to no previous points unless it was exactly identical to the first one. And that's kind of what we're trying to avoid. And instead, if we work with local surrogates, so in this case, I've depicted a one reduced density matrix. So if you kind of take a single qubit and average out the rest, then this could be a reasonable proxy for something like similarity between two systems, even though it's not kind of the overall fidelity. And in fact, we show in the paper how to use classical shadows, or in the appendix, to do arbitrary orders of RDM where you can kind of dial between them. But for this, for simplicity reasons, we can also add then, I mentioned before how even slight changes to the kernel boost the power of the functions you can learn. We'll take a tip from classical machine learning and use something like a squared exponential, which in principle allows us to express and learn arbitrary functions of the one reduced density matrix. And this turns out to be very powerful, very trainable. And I think it's an interesting open question that I list at the bottom, where we spend a lot of time in chemistry and certain areas of physics talking about in density functional theory, due to certain universality in the interactions, the density alone, and by extension, the one RDM, is sufficient to tell you everything you need to know about a system. So what do these universality results tell us about the power of even the simplest rung of these embeddings? And I think that's an interesting question to ask, what can be learned on quantum space, particularly in regards to results I'll briefly mention at the very end. So how do we actually make progress on this abstract problem? So we're going to introduce this kind of central bound, which I'll break down, which is a learning theoretic bound. In particular, I've trained some model, and now what can I say about the error on the examples I haven't seen yet, assuming I draw X from this data distribution and the same distribution between the training and test examples. And this H will be my fancy learned model that probably comes out of the kernel method. F is the truth. N is the number of training samples. So this should help you keep in mind that even when there's big separations, at some point, there's enough data where this gap can be overcome, perhaps by a classical device. And the central quantity tells us how big this gap is. So intuitively, it's a measure of how good a predictor this kernel is. So if the function values are close, then this similarity measure should be close as well, which makes SK small. And basically, this is kind of the definition that exists in the paper, but I'll move on from that. And so you might say, okay, but don't I need to know a lot about the function itself to say anything? And surprisingly, this lets you say something fairly quickly about not the specific data you're interested in, but in fact, all possible label functions that you might be trying to predict on. So if I have some classical kernel and some quantum kernel, so this is a similarity measure between my input points, like how similar are the Hamiltonians, how similar are the states. One is efficiently computable classically, one is efficiently computable quantumly. And I can say, just based on these kernels, how well they'll perform relative to each other. So when this similarity measure is small, then no function f exists where quantum outperforms the classical. And when it's large, then some label function exists where quantum has the edge. And of course, this doesn't mean that I can easily say something about all possible classical or all possible quantum. What it means is kind of a very nice heuristic method, for example, for taking a quantum kernel that I think will be very powerful in its associated data. I write down the implied kernel on the data set. and then I take a string of classical competition, simple methods like squared exponential, kernels, things like that, and I quickly screen through them, which is often quite fast by comparison. And if I find any classical method where there's a small GQ, that means that the classical method is going to be as good as the quantum one, and I probably shouldn't use the quantum one. And in fact, this then also gives me a simple method once I've found that minimal geometric difference to saturate this GCQ and predicts the amount of training data that I'm going to need for the classical one to close the gap. Because if you remember on the previous slide, there is some gap that can be measured between the quantum and classical ones that I've located at least, but it's also implied that with enough data, I can always close that gap. And how much data is required is kind of the interesting part. So let's go on to how well it works in practice. I think an example is probably best. So we'll take something like the fashion MNIST data, and we're going to compress it down and get some length in vectors. So I'm going to get it out of the principal components. And basically for each one of these fashion MNIST photos, I'll be able to dial how much input data I put in, which will correspond to number of qubits. And I'm going to try a range of embeddings where I try to make the embeddings more and more quantum. And basically, what this is going to mean is that I would like some kind of classical baseline for no entanglement, and then I would like to make things seemingly more and more quantum to figure out where this dividing line lives. Like, when does quantum actually have a chance at doing better than classical? So for the simplest case, I'll just do uncoupled rotations. For the second one, I'll do something like IQP circuits. And for the final one, I'll do some kind of crazy non-converged Heisenberg evolution that hopefully is very, very quantum in the way that it spreads entanglement and does things without going all the way to random. And I'm going to try a few different labels. So the labels are going to be, I'm going to either predict the original fashion MNIST, or I'm going to then look at quantum, which is an expectation value that's kind of the expected value of this Z operator that actually includes the embedding that I'm mentioning. So this is going to be a little bit stilted for quantum. And finally, I'll look at totally engineered data, which is very, very stilted for quantum. And what will my classical competition be? It will be many things. Deep neural networks, Gaussian linear SVMs, et cetera, et cetera. And so what do we find for these particular embeddings of these data vectors? So first, we look at this geometric difference, which I told you, independent of any label function I look at, tells me this maximal separation between the quantum and classical performance. At 1, I should always be using the classical method. And as you go higher, more data would be needed to bridge the gap, but quantum might have an advantage in a limited data setting. And PQ is this projected quantum kernel, while Q is that original quadratic quantum kernel. And so you can see that for the E1 embeddings, no matter kind of what you do, this separable rotation, things kind of lie along this bottom-ish line, or not very high, because the quantum and classical, they're kind of easy to predict. And then for the others, you need this kind of getting away from the fidelity-based metrics to have any data at all. And then, okay, let's look at the actual label functions. So that previous graph for the geometric difference tells you about the best possible separation. But let's actually look at what happens when I look at, say, the classical data set in this bottom right-hand corner. You find, so these graphs have prediction error in the classification for this one, so higher is worse. And basically, you find that while the projected quantum kernel does about as well as classical, there's not really a reason to choose anything other than classical in this point. So that you might have imagined beforehand. And now let's look at the more stilted data sets. So in this case, the data set includes the embedding, as I said. So the quantum actually has a fairly substantial leg up over the classical that has no information about that. And even still in these cases, for the first one, this separable rotation, the classical machine learning pretty much nails the problem entirely. Now I make things a little more quantum in E2. And this is these IQP circuits. And now there's a little bit of advantage for the projected quantum kernel, but it's kind of very slight. And you can imagine a little bit data would help you. And now we finally do this kind of Heisenberg evolution, which was crazy. And even then, we only get kind of a marginal separation. And you might worry that with additional data, this might shrink as well. What's the takeaway from this is we tried really hard to make quantum data sets that were kind of naturally quantum from some base data source, in the sense that they're generated by very quantum evolutions. And when we looked at the results, we found that given a bit of data, classical machine learning was often still incredibly competitive, if not better in some cases. And so we wanted to tip the scales even further at this point. We're like, okay, well, does any data set exist where you should use a quantum computer? And we used this engineered data set that I mentioned. So you can perform a maximization over all label functions to make it as hard as possible for any pair of quantum and classical kernels. And even in this case, so with E1, where that geometric factor was small, classical is just as good as quantum. And this graph also includes, as we change the data points, how much it improves when you go from 100 to 600 training data points. In the moderate case, you can see some advantage for the quantum case in this case. In this case, accuracy is better, so higher is better, the reverse of before. And finally, in this very quantum, very stilted case, you can see a sizable difference between the quantum and classical, which tells us perhaps that there exists some data sets where there is a substantial advantage for quantum in a limited data case. They're in fact very hard to create. And it's an open question where you would find such a thing in nature. And so I wanted to mention, of course, that making sure all of this actually works. So there was a lot of previous studies on kind of quantum machine learning that if you go up to say 2 to 4 qubits, you can make conclusions that are maybe not as accurate as you'd like them. We wanted to go as big as possible. And for that, we thank TensorFlow Quantum and Michael Broughton for helping us get to an exaflop of total compute to work on these numerics. And then I wanted to mention very briefly before I close a few other recent results that are not mine, but I think tell us something about the future of learning and quantum machine learning, which is kind of shortly after this work, the same first author that was working on this power of data work that I just presented, wrote a paper on how, in fact, many problems in ground state prediction for physics, so local observables and other things, are also in some sense provably easy once you have a few pieces of data from that same phase. And chemistry, though, a little more discrete in these properties. It's interesting to ask, do these results apply there? And then if you kind of take all of these lessons in, are you left wondering if the fate of quantum computers is to provide training data for classical models? Because while that would be useful, I don't think that would be super exciting for most of us here, for one of the most advanced technologies humanity has put together to date. And so what's left for a quantum computer, I'll end on a positive note, is that some recent results have shown that with as few as just a couple copies of a quantum state that you can keep in memory, meaning if you have a source of state, say from nature, that hands you one measurement of the state and then you wait and get another measurement, in some cases you can extract exponentially more information, meaning the same quantity can be learned to that precision with exponentially fewer samples. And I think this is kind of an interesting and unique phenomenon that hasn't been explored enough yet in the realm of quantum sensors and learning from that quantum data. So just kind of taking a step back, now I'm taking another look at computational chemistry. And I took you through kind of a roundabout route that said data from quantum computers can sort of lift classical learning above its direct simulation competition. But that starts to look a lot like things we already do in physics and chemistry when we look around and use data to make interesting approximations. And many problems in design, synthesis, and biology, I didn't talk about this as much, feel like undecidable chemistry problems, but what can we say about the way data from nature helps us? Is the fate of quantum computers largely to provide data for classical machine learning? And I think the answer to that is perhaps not. But I leave it open to people here to think more about those questions. And I, in fact, wrote a whole philosophical perspective on this that many of you invited me to speak at the Simons Foundation, which you can learn more about if you would like to check it out at this archive link, where I wanted to take a very different tact from the idea that molecules simply are encoded in quantum computers and produce solar punk utopias, but rather to see where are the edge cases, what problems and what quantum computers can teach us about this science more generally. And so just to summarize, taking you through kind of this philosophical perspective, a computer science perspective, and just a practical tool for understanding how we might reach advantage in this learning problem. And as I mentioned, I don't know that this takes us a step forward in reaching quantum advantage, but rather allows us to understand that the competition in beating our best classical methods might be harder than we think if we attribute some amount of power to the data we collect in labs or the hypotheses that we generate on our own. And with that, I'd just like to thank those most closely involved in what I talked about. Robert Wong did a lot of the technical and proof work that you saw. Michael Broughton scaled things up, and all of the people at Google Quantum AI for helping out in this. With that, I'd like to thank you all for listening, and it looks like I have left enough time for the question session. Excellent.
Thanks so much, Jarrod, for that super nice talk. I think you're still sharing your screen, which you can probably...
Yep.
Okay, awesome.
Close that for now, unless there's a specific slide-based question.
Yeah, sounds good. Yeah, thank you so much. As Jarrod said, now it's would be great to open it up to questions. So yeah, if anyone has questions right off the bat, I'll try to keep open. I'll try to pay attention to raised hands in Zoom and stuff. But Umesh, sounds like you maybe have something you want to say right off the bat.
Yeah, nice talk, Jarrod. So, quick question. Where you compare best machine learning algorithm to quantum speed up. So, well, this notion of best machine learning classical algorithm is always a fraught notion. So, what does that mean in your context? Yeah. So, could you say a little more intuitively about where you feel the speed up is coming from, or do you have some understanding of what's going on there?
Yeah, so let me mention briefly what I mean by best machine learning algorithm. So for us, we kind of try to outline this. We try to be as clear as we can in the paper, but of course some things will be lost, that we mean it in a very practical sense. So we define this distance metric between some method that you choose and the quantumly and one that you choose classically. And of course, optimizing over best classical would be incredibly hard. We don't know if we can say anything really about that. What we do in practice is take for each problem and try out like 10 methods with aggressively tuned hyperparameters and report the results from the best classical one that we can find. And very often what we found when we did that was that the classical ones were essentially always better. We in fact had to work to make ones where the quantum showed some amount of difference. And so what gives it the leg up? I think there's kind of an uninteresting question. There's an uninteresting answer and an interesting answer to this. And I don't know that I have.
May I ask a question before that?
Oh,
yeah. So when you say I mean, I meant it in a practical sense. What does it mean practically? I didn't expect that here, a proof or anything. But I had the following in mind that that I assume you have a small library of algorithms and you try them. But then when you look for this distinguishing algorithm, then you're putting in some thought or effort into saying, okay, let me make this one perform better than that. And so at that point, your library of classical machine learning algorithms, of course, have been tuned for natural examples. And so is there something to think through there? That's what
so you mean when you start to fit, I think maybe this segues into what I was going to mention for the more interesting answer, which is if you start to train over natural data sets, do you pick up what's sometimes called an inductive bias with relationship to natural physical data, which is to say that when you get new data, you're inherently biased towards physical solutions, which gives you more predictive accuracy than something which just approximates all functions randomly equally. And I think this is a super interesting question, and there was a paper not too long ago about inductive bias in quantum kernels, but a lot of the results there were showing that if you took random functions, these didn't have the biases that you want. And I think, in fact, the most interesting directions in these data embeddings is understanding how either the training, the embedding, or kind of the models, as you say more generally, tilt you towards physical systems. Because the paper that I mentioned towards the end of Roberts, where they showed that kind of ground state property prediction was easy. They did that in the less interesting case of basically with enough data and smooth functions, you can fit anything, but it doesn't lean on anything from inductive biases. It's basically like a Fourier smoothness argument. And so I think that jump from fitting any function to fitting physical functions is super interesting, but I don't know that we know a lot about it yet.
May I ask a question on also on the speed up? So I think most of us are hoping maybe for some kind of exponential speed up or quadratic speed up. So the current take-home message is that asymptotically speed up may not even be possible. So is that the case? So I mean, for the different data set that we have in mind, we may not have any kind of asymptotic speed up, and even maybe this constant scaling speed up could be questionable. Is that?
Well, I would say that this might actually be worth considering a different form. Sorry, the train is going by. 1 second. But this might be worth considering a different form of speed up. So normally we think of course, like asymptotic speed ups as maybe quadratic is a little bit too slow, even because of overheads due to error correction, and we try to think about bigger and bigger speed ups. But here it's kind of a different problem. So if I'm collecting data from my environment, and I can only get so much data either due to the amount of time available or some kind of source being inaccessible, then in fact a constant speed up can be better than the ones that I had for other problems, simply because no classical computer can make up the difference. When the data is kind of cut off, I can't take samples that allow me to do the same things that I could do in the quantum case. So here I'm kind of implicitly talking not about embedding classical data into a quantum computer and then reading out the results, but rather getting data from an actual quantum source. And so there, I think there could be a fairly substantial advantage, but it's a little more fraught when you're embedding something that, yes, in exponential time, you could simulate it, but there may be other structure as well.
Yes. So would you say that the bottleneck is more in the input and output instead of the, say, the optimization or this kernel framework? More in the, so I mean there are many steps. There are many steps. So I would like to ask what is exactly is the bottleneck here in this quantum machine framework? Is it, say, the input and output?
The bottleneck for the quantum or the classical
machine learning, quantum machine learning.
So the bottleneck should, I think the right place to think about it is kind of the collection of data that allows you to learn the most interesting functions on the space. So if the features that you are given are easily related to the outputs, like as a linear function, then there's no advantage to using a quantum computer, obviously. If that input comes in the form of a quantum state, and that quantum state has kind of very non-local correlations in it and different bases, then having even a few copies of a quantum state, you can extract information and do learning tasks, which are much, much better than what you could do with just single copies at a time. If you're in this third case of kind of information coming in, that's classical, I encode it in a quantum state. Now what needs to be true is that this embedding was both hard and geometrically much more natural than anything else I could have done. And so that's kind of where the bottleneck and the sample separation has the potential to grow, but does not always grow, as we saw from the data.
Thank you.
Hi, Jarrod, if I could ask a question.
Sure.
From what I saw from the graphs, it seemed like the projected quantum kernel was really the only instance that gave a good advantage. Was there the actual kernel that ended up being useful? Did you check if that kernel can be calculated classically? Because in that case, it seems like it could be possible.
So we know that in the general case, it cannot be calculated classically efficiently, but in kind of the cases that we looked at, we did not try to press for these particular embeddings to be hard classically. So one slide I took out is there's kind of this other hard open problem related to this, what I would call sort of a Goldilocks principle of quantum circuits. So when they're very short, they're very easy to approximate classically. That was like that for E1 I used, and E2 is definitely easy. And then on the other hand, you have like the quantum supremacy type circuits, which are very long and very random and hard to sample things from. But when you look at expected values, they all concentrate. And so those are also easy. And now somewhere in the middle, there's got to be something that's hard to simulate, but provides also signal on those reduced observables. And I would consider that still a hard open problem that's more or less equivalent to what data that we simulate quantumly is sort of naturally quantum in this sense. Like if I do a quantum simulation problem of a very physical system and learn on that data, is that actually more quantum than just learning that data classically? I think is hard, yeah. So.
Gotcha, thanks.
Mm-hmm.
Do we have any more questions? I guess I'll pause for a second and see if there's any more specific questions about the talk, but then I think we can talk about some slightly broader questions, zoomed out big picture stuff. Was there anything else before we do that? Cool. If there is anything, you can feel free to put it in the chat and then we'll get to it. But yeah, Jarrod, I think it would be nice if we could chat for just a minute about some of those questions we were talking about before. Just these questions of like, from a broader picture, what are the biggest next steps? And what do you think, are maybe the obstacles to getting to the next stage in this sort of thing, and broadly questions like that. So I don't know if you want to, I can ask something more specific, but I can just kind of give you the floor to talk about that if you want to right off the bat.
Sure, yeah. I think I can talk maybe first about learning and then a little bit about the other big open questions. And you'll have to stop me if I start just rambling, because I want to make sure it's interactive. But from kind of the learning point of view, I think, especially for these kernel methods, the question that Babak was getting to was one of the big interesting ones, which is we did a lot of these studies of, first we came up with this geometric metric, then we did some kind of formal separation between having data and not having data. And then we tried to give some practical intuition and push things for finding cases where quantum computers offered you some advantage in the embedding. And of course, the provable example you can point to for this is factoring. But we'd like to get a better intuitive sense of when you can embed data via a quantum circuit, read something out about the geometry, and this problem is much more naturally suited to a quantum computer. And I think some interesting ways to kind of pursue that might be to look at the most quantum things we know how to simulate, so maybe strongly correlated systems, and try to figure out when that geometry helps us, when it hurts us, what good circuits look like, what good embeddings look like. And I think that's a very hard and open problem. And kind of you'll notice I didn't spend a lot of time talking about the quantum neural networks part, because we actually managed to slump all of the part of the classifying circuit into the hard work of the classical kernel method. So it did all the heavy lifting for us. And in fact, we found that that was a prudent strategy because it was incredibly hard to train some of these variational circuits at the end for the tasks that we wanted them to do. They were fraught with local minima. It was a big deal to kind of get them to classify anything. And there's actually an open problem there that is not often talked about, which is in the training of quantum neural networks, as we call them today, though their resemblance to classical is perhaps optical at most. Classically, one of the reasons people really like deep networks is the backpropagation algorithm. And so people will be like, oftentimes physicists will look at backprop and they'll be like, oh, big deal, you learned how to calculate gradients. We've been able to do that forever. But actually, the important part of backprop is not that you know how to analytically calculate a gradient. It's the dynamic programming part that reuses information that makes function evaluation exactly as expensive as gradient evaluation, up to a factor of 2. And in the quantum case, we often pay number of parameters, so we're quadratically worse than that. There are some quantum algorithms that'll boost you to only a factor of n to the 3/2 worse, but that's a pretty big gap. And is it fundamental? Can we not reuse information because of quantum measurement? Or are there some of these other, gentle measurement schemes that can get you around that? And you're like, okay, big deal. factor of n squared, who cares about that? Well, it was kind of the determining factor in going from big data. So kernel methods compete often with deep neural networks. Kernel methods often have some hidden quadratic scaling, and deep neural networks, because in part of backprop, you can often make almost linear in every parameter or sublinear. And so it changed what everyone used for big data. And so we're at this kind of tipping point where, do I lean in kernel methods or do I go for deep neural networks? And if so, how do I say anything about quantum dynamic programming? Is this an insurmountable measurement problem? So that's the learning topics. Maybe I can say what else I would, unless someone wants to chime in now and ask about either of those. Perhaps not.
It's not, yeah. So go for it.
Yeah, the other thing I spend a lot of time thinking about these days is, I think it's very important for the field as a whole to do something interesting with quantum computers that are between 100 and say 10,000 qubits. And right now, the only feasible proposals that I have seen for doing this and getting something other than random noise out of the end are error correction. And so I'm being a little bit flippant to hopefully provoke an answer if someone has an alternative, but it's going to be not so great if we do something like a beyond classical demonstration with random sampling at 50 qubits, and then we have 100, 1,000, 5,000, and now we're doing like Clifford gates. And so when people ask, oh, you now have 1,000 times more qubits, what can you do? It's like, well, even less than before. People aren't going to be super excited. And so I try to think a lot about what are good, interesting ways to try to get two applications on 100,000, 10,000 qubits. And of course, anyone here who's tried to do it knows the big problem is we have a lot of noise in our particular operations. And of course, people are coming out with error mitigation methods, but you can just construct a very simple argument that if I could tell you every time there was an error in the system, the best thing I can ever do has a pretty hard exponential wall, and you can calculate the sampling time based on how quick your device is, and you're like, okay, I can only ever do 1,000 operation circuits if I want this accuracy. Like, okay, well, how do I break these assumptions? You need to start doing non-unitary things. You need to start measuring, resetting, feeding forward. But how should you do that to be actually useful? How do you construct useful algorithmic primitives that don't just splay things to the wind and hope for the best? I think this is a very important problem for starting to have any proposal which has a chance of running on 100 to 10,000 qubits. And I think it's critical for kind of the excitement to stay high in the field that we're able to use these devices in interesting ways, which, by the way, is not to say that quantum error correction is not interesting. I think it's one of the most fundamental and interesting things we've learned about quantum physics from quantum computing. But I think for other reasons, we're going to want to do other things as well.
Awesome, thanks. Yeah, that actually brings up a question that I was kind of wondering, which is, so, and maybe I kind of missed this, but maybe if you can, if so, you can say it again. But the question is, so I remember, I think it was at the end of your paper, you kind of mentioned that this sort of thing could potentially be used as sort of like a efficiently verifiable test of quantum advantage in some sense, because you can kind of like do this sort of thing and then see if the results you get actually make sense. And that's like kind of exactly what I work on, is trying to come up with efficiently verifiable tests of quantum advantage that we can run in the near term. So I'm really curious, what you see as the main obstacles to using this sort of thing as that sort of test, and how that sort of landscape looks.
Yeah, so I think maybe what we're referring to is if you're allowed to sit in this regime of kind of data sparsity that we were talking about before, like I'm going to give you 1,000 samples of a quantum state and no more. And now afterwards, I'm going to ask you a series of questions where you kind of know the family of questions, but not the specific one I'm going to ask you. And you can construct problems which are relatively simple that demonstrate an exponential advantage in this setting as soon as you get to 2 copies instead of 1. And basically, there are not really any barriers to doing this if you allow yourself one of these kind of prototype experiments where you say, prepare the state on a quantum computer, and now I pretend that I can't see the first part of the circuit, and the problem becomes receiving the state at the other end of the circuit. You might find that interesting, but maybe a little less satisfying than if we could do it in the natural world. So the question becomes, okay, if I had data from sensors, how could I have a similar problem set up? And you kind of look to what the features of the quantum state were that comes in that gives you this advantage. So the state need to be in classical correlations in the density matrix. And so like, okay, well, how do I get this into my quantum computer? So I need to like transduce the state. And so that seems a little bit sci-fi. But if you're already working in a system where your sensor medium could be the same as your computational medium, and I'm looking at ion traps or neutral atoms that have already been very successful in both camps, perhaps separately, maybe you could do something there where the measurements that you get out, you now are able to learn things about your system that if you did it with the typical one copy sensor, you would have had to run an exponential number of samples. So that was a bit of the timeline of what gets in our way for verifying that, but maybe that's answers your question.
Cool. Yeah, no, that's super neat. Thanks. So I guess with that, actually, maybe maybe it's time now that we should kick out all of the PIs, et cetera, and have kind of a students and postdoc chat for a little bit. So yeah, if the PIs don't mind logging off now, then we can just have a little chat among students. I guess it's in progress.